So we talked about the mathematics of what happens when a parcel of air lifts, and now we're going to bring in something else, environmental temperature. But before we do that, we need to add one other complication to this already convoluted graph here. It's the skew T. All the information is the same from the previous graph, except the temperature lines, which are right here, are skewed. So, in other words, they're not straight up and down. And if we were to draw a straight line going up, this would automatically get cooler. See, this is the 20-degree line, this is the 10-degree line, 0 degrees Celsius. The only reason for this is so that more information can be conveyed on the diagram. So just to reiterate that, on this temperature line here, this red line, even though this point and this point, I'll make them the same, even though those 2 points are on the same vertical line, this one is at 10 degrees, and there it's about 15-ish degrees. So temperature lines are skewed. You still have the dry adiabat lines going this way. You have the constant water vapor content lines, and you have the moist adiabat lapse rates there. All the information is still there. Hopefully that all makes sense. And this image, by the way, this is taken right out of the FAA Glider Flying Handbook. They distribute PDF copies for free on the internet, so thought it would be fine to just take a photocopy of this image here. Now this red line right here that you see, that is the environmental temperature. Okay, this has nothing to do with the sketches we were making in the last video of the different temperatures at different heights when a parcel lifts. This is the actual temperature of the atmosphere measured by a weather balloon. And this green line here, that's the dew point, the actual dew point measured by a weather balloon through the atmosphere as it goes up. Now, if we were to lift a parcel from the surface, and this is the surface right here, the ground, the bottom of these lines, we're assuming the balloon is obviously launched from the ground, what would happen to the parcel as it lifts? Well, then it would follow those temperature and dew point lines that we discussed. The temperature of the parcel as it lifts would follow the dry adiabat, and until the constant water vapor line meets the dry adiabat, and then it would follow the moist adiabat line as long as it continues to rise. And remember, the parcel is an isolated system. So as a parcel is pushed up through the atmosphere, a parcel that originated from the surface, this is the temperature that the parcel would have. And that has nothing to do with the actual temperature of the environment. The parcel is its own system. That's the point of this. The parcel does not mix very well with the outside air. That's a pretty good approximation. You should also know that parcels don't just originate from the surface. If we, let's say, had a parcel that originated from this level here, it would have this temperature at first, this dew point at first. As the parcel lifts, it would follow the same idea. Dry adiabat for the temperature, constant mixing ratio for the dew point, until they meet at its lifting condensation level, and it'll, if it continues to rise after that, it'll follow the moist adiabatic lapse rate, forming a cloud. And the thickness of the cloud, it'll be condensed as long as it continues to rise. Its temperature and dew point will be on top of each other throughout the remainder of its ascent. So what I wanted to get into, what will cause a parcel to rise from the surface or from anywhere? The answer is buoyancy. If you let go of a helium balloon it will go up because helium is less dense than surface air. Obviously, we're not going to get a bubble of helium at the surface, but we could get a pocket of air that's less dense than the surrounding air. And this can be done by heating. In the first video, we discussed how temperature, or warmer temperatures have, or warmer air, the molecules are moving faster and they spread out more. So warmer air is less dense than cooler air. And so remember that. That's a key concept. Warm air always has a lower density than cooler air. Assuming you have a constant pressure, but as we go up, that's the comparison levels are going to be constant. So that's the concept we need to remember, is that warm air is less dense than cool air.